Okay, good morning. Alright, so some of you already had your lab yesterday, so you collected your stuff. Alright, so like I said, those of you who haven't, you collected on Friday. Okay, so important thing is the board. The board is very, very important in the sense that we only have limited boards. Okay, so I've just put out an order for additional boards. Okay, because I think yesterday those who came for the lab tested, so the board is fine, it's working. Alright, so I just put out another order. So we have some spare that we can use, okay, in case the board gets damaged. Alright, but again, be very careful. Alright, so you need the board for all the labs, okay, and as well the project as well. Okay, so you will see some pins there, alright, where you need to solder the header pins, okay, but you don't need to do that now. Alright, so for next week's lab, you don't need the header pins yet. Okay, next week's lab is still just the board as it is, and we do some coding first, okay, to be familiarized with the board. Then subsequently you do the soldering. Okay, so for the soldering part, you wait first. The next lecture I will brief you on what to do. Okay, so no need to rush and do any soldering for now, and keep the board and the components safely. Alright, so for the first few, for next lecture, next lab, you just need to bring the board alone is enough. Alright, then subsequent labs you need to bring other stuff. Okay, so once the new boards are in, I will try to distribute extra board for each group. Okay, so currently we have one board per group, okay, or one team. Okay, once the new boards are in, I will distribute 2 per team. Okay, so you have enough to share. Okay, so today's lecture onwards, basically how we will do is, I will cover the lecture part, the concept, what we're going to be focusing on, and then after the break, we will have the review of the lab, okay, and the code associated with the lab, so you understand what you're going to be doing in the next week's lab. Okay, so it gives you sort of a preparation, okay, and understanding of what is going to happen when you do the lab. Okay, so let me finish up this topic first. Okay, this is actually from last week, software design, for us to have some understanding of where we are right now in terms of how we write software and how it translates to the hardware resources that we have. Alright, so concurrency. Okay, so what is the concept of concurrency? You want to be able to do multiple things at the same time. Alright, can we already do that? Yes, we can. Okay, in EPP1, EPP2, we already have concurrency, but that concurrency is because of our hardware. Alright, so if you remember when I used for example, my timer module, okay, to generate some periodic timer interrupts or to generate some PWM. Okay, what am I doing? I'm configuring the hardware, okay, doing some setup, and once the hardware setup is done correctly, the PWM just comes out, correct? I don't need to write any more software or do any more code to make the PWM happen. Okay, so that is concurrency, because you are able to do execute your code while the PWM is managed by the hardware independently. Okay, same thing, I can also set up my ADC, okay, in your Arduino, okay, in EPP1, EPP2, where you say that I set up a periodic timer, every 100 millisecond I trigger ADC, the interrupt will notify me when the ADC is complete, I can capture the value and do something with it. Okay, so the idea of concurrency has already been there. Okay, but the only sort of limitation we have is because we are using interrupts, okay, which are tied to the hardware. Alright, so you are limited in a sense by the amount of hardware resources and interrupts that you have. Okay, so this is an example that we also saw last week, where I say I can use a timer to set up maybe an interrupt, so I can say maybe every 100 milliseconds generate some interrupt for me, and after the interrupt is triggered, in the timer ISR, I go and start the A to D. Correct? And when the A to D happens, once the conversion is complete, I will generate some interrupt. I can capture the value, put it into some variable, okay, and then I set a flag. Alright, so the main loop knows that the ADC is complete, and then I can use the ADC value. So what is happening in this entire time here? Am I waiting for anything? No, correct? I am able to do other things. But I am able to do anything else in that time gap while I'm waiting for the conversion to complete. So that idea of concurrency is already available to us. Okay, so in a sense, all right, we use this idea, all right, of interrupts, okay, to achieve concurrency. Now, how do we make the processor more responsive or be able to do more things? All right, so that idea of interrupt is what we have. All right, so this is just to recap what interrupt is. Correct. So we know that while I'm busy doing something, an interrupt is triggered. Then in that concept of interrupt, I need to finish up certain activities. Correct. Okay. That other processing is what? Things that I am currently in the process of doing and I need to finish. Okay, that means the processor is already started and I need to finish it. Okay, and then I do the context save. Do you remember what is context save? And context restore, that means I need to keep a snapshot of where I'm currently stopping, correct? Because when the interrupt happens, you are busy doing something else. Okay, so I need to keep a snapshot of what I was doing. So when I say a snapshot means what? What do I need to remember? I need to remember where I was executing, alright? You all are doing assembly language programming now, other module, 20, 28 or 20 something like that? Or yet, or done already? Done already, correct? What is the module? Forget already. Burn and throw already, right, the notes. Which is the module you learn assembly language? Hey, don't look at me like talking Korean. Which module you all learn assembly language? In this semester? Or you're going to learn it in this semester? Oh, okay. So you haven't learned assembly language yet? Sure or not? Don't bluff me. I'll go and check. Sure? Haven't learned assembly language yet? How come? You all are year 3, right? Something is wrong. Okay, assembly language will be taught in year 1. Okay? Okay, maybe we need to rethink the curriculum a bit. Okay? Alright. So assembly language is very important. When you want to learn embedded systems, you need to know assembly language. Okay, because assembly language is what ties you to the hardware. Alright, so you need to know what is happening at hardware level. So when you say context save means you need to keep track of where you left off. So when you write code, you need to keep track of which line of code you're executing, correct? Alright, so that one is a register, okay, called PC. Anybody know what is PC? Program counter. See, you all know what? You all heard this term before, right? Program counter. Program counter keeps track of where you are, correct? Then you also have your internal registers where you keep your data. Then you also have your stack pointer, alright, where you have a separate memory area for your stack where you push and pop data, correct? To save and restore. Okay, so these are all these registers, okay, that is tied to your execution of your code, which you need to save, correct? Why you need to save? Because you need to come back to this place, correct? After the interrupt is finished, you need to come back to this place. So you save, okay, then you do whatever you need to do, okay, and then finish, you restore, and then you continue. So this is the idea of interrupt. It's the same thing. Any controller, whether it's Uno, whether it's this Atmega, or any controller, the idea of interrupt is the same. Okay, and this idea of context switching also applies to tasks. Okay, so later when you bring in the OS, it's still the same thing. When I'm running one task, when I want to switch to another task, I need to save my context. So that when I switch, and I want to switch back, I know where I left off. Okay, so now how can I schedule? So we're just going to go through some concept of how we can schedule interrupts, okay, and the whole system. Alright, so let's look at this example again that we saw before. Alright, so in the last lecture we saw this, where we have a simple device where you want to monitor or track how much rotation your wheel is having, okay, while you are doing some cycling. Alright, so how can I program it? Okay, it's up to you, correct? You can have different ideas. So one way I can program it is, I can say that I use interrupts for everything. Correct? So my button, okay, to select the display, to change what I want to observe, I can use a button. When the wheel is rotating, I can put some sensor that can send pulses, correct? Okay, so whenever the wheel is rotating, I can send some pulses and say, okay, whenever the positive edge or negative edge is triggered, I generate an interrupt. So I know that I've completed one round or something like that. Okay, and then to keep track of time, also I can use a timer interrupt. Okay, so I can sort of solve this design using just interrupt, and in my main code, okay, this is basically your sort of setup code. Correct? So in my main setup code, what do? I just need to do the basic stuff. Okay, so before anything, just a reminder, the poll is always active. So if along the way you have questions, you just put, then I'll see here. Then we can discuss those questions. Okay, so this is the one way of designing this system. Alright, now let's look at a more complex solution or complex application. Okay, this is a GPS-based pothole alarm system. Okay, in Singapore, do you see a lot of potholes? Not many. You know why? Very simple, because people like me who drive pay road tax every 6 months. Okay, so got a lot of money to fix all the road holes. Okay, so the government is very good. So they collect the revenue, but they do a good job, correct? They make sure that the potholes are clear, the drainage system is good. Okay, the trees are cut, so everything is good. Okay, but in other countries, maybe the maintenance is not so sort of up there yet. So you have this device or this system where you have a way to detect potholes, so that, or you know that there are potholes nearby, so you don't want to go over them. Okay, so let's look at some basic tasks for this pothole-based detection system. Alright, so firstly, I want to decode. Alright, that means while I'm driving the car, I want to decode to know where I am. Alright, so that is based on GPS. Alright, so after I know where I am, I need to sort of check my location with the database, correct? Whether there are any potholes nearby. Alright, and then whenever I want to update any information, so for example, I detect a pothole that is not there, I can say update. Okay, so I want to update the system to say that there is a new pothole that is detected, then maybe I have some simple UI, some switch, some LCD or GUI or something like that. Okay, how do we schedule these tasks? So I have all these tasks. Okay, I have all these tasks. Now how do I schedule them to achieve this objective? Alright, so let's look at it as a very simplistic way. So the most easiest way is I just say I do everything sequentially. Okay, I do everything sequentially, which is basically called a cyclic executive. Okay, that means I do task 1, task 2, task 3, task 1, task 2, task 3, task 4, task 5, and the whole thing just keep repeating itself. Okay, so it's a very easy, straightforward way. Okay, everybody can code this and get the job done. Okay, now what is the issue with this? Okay, it works very nicely if your GPS data comes directly in the beginning, correct? Okay, but this is something that is out of your control. Correct? You do not know when the next GPS packet will arrive. So if your GPS packet arrives, for example, at a point where you are doing this record function, then what happens? By the time you decode this GPS data and realize that something is wrong or something needs to be averted, it is quite late already, correct? Because you need to wait for one full cycle from here all the way until I decode the new data here and check against the database. Okay, so it's sort of not very ideal because you do not have control over when the new GPS data arrives. Okay, so this is one of the issues with this kind of a sort of static schedule that we may normally have. Alright, so what can I do to improve it? Okay, I can say use dynamic scheduling. Okay, dynamic scheduling means I assign some importance or priority and then I adjust the sequence accordingly. Alright, now of course there is also two types to it. One is called run to completion, the other is called preemptive. Okay, so what are these two? If I say run to completion means if the GPS data arrives. So we know that for this system, decoding the GPS data is the most important thing, correct? Because that is the latest information that tells me where I am. Alright, so the moment the GPS data arrives, I need to process it as quickly as possible. Alright, which means that if the GPS data arrives while I have already started, so I already started this, but it comes in a bit later, correct? It comes in a bit later, but I know this is important. So if I say run to completion means I complete what I already started. Okay, and then I switch to analyzing the GPS data. I decode the GPS data. Okay, so that is dynamic sort of scheduling because I rearrange the sequence based on when the new data arrives. Okay, so of course a better version of this, okay, would be I preemptive. Okay, I preemptive. That means when the GPS data arrive, I can immediately stop what I'm doing and straight away switch to decode. Okay, so this is a better version because I may have started it, but the moment the data arrives, I switch to the most important function, which is decode. Okay, so this sequence of scheduling, okay, so I skip one slide, let me go back to that slide, is basically what we call managing the task state. Okay, so this idea of task state will become more clearer when we switch over to the OS side. Okay, but the main idea is you have a sequence of tasks that you need to execute. Okay, so in our case, what are the sequence of tasks? You need to decode, you need to check, you need to record, you got the switch, you got the LCD and so on. So these are the tasks that I need to execute, and you can say that the tasks can be in different state. Different state means what? That means I can decide who is going to run first. Okay, who is going to run first? Alright, so if I choose to decide and say, okay, decode is going to run, then that task will go to running state. Okay, while the other tasks are waiting in the queue. Okay, but at any point of time, okay, I can decide to switch it around. That means I can say the decode go to wait while somebody else take over. Alright, so this is a sort of introduction to this idea of task state. Okay, but this task state we will revisit when the OS come back. Okay, then you will have a bigger idea of how this whole thing comes together. Okay, so coming back to this, you can see that if I look at the response time, alright, the static scheduling, okay, which is the easiest way, works. Okay, it works, but in this particular sort of use case scenario, it is not so ideal. Okay, because of the time that you may wait when the GPS data arrives to the time you get the updated location. Okay, then the dynamic one is of course better, and the most ideal one is dynamic preemptive. Alright, so of course these are easy to sort of conceptually talk, but when you want to actually implement it, it's not so easy. Correct? You need to think of ideas of how to implement this scheduler. Alright, so cyclic executive is more easy, straightforward. The dynamic one is more complicated. Okay, so let's look at how we can come up with some idea of this coding structure. Okay, so the cyclic executive with interrupts is what you are already comfortable with. Okay, it's what you've been doing with the Arduino Uno in the past, where you have some main loop, okay, where you have an infinite loop, and what do? You may allow the interrupts to set some flag to tell you that something has happened. Okay, so I can have multiple interrupts for different devices, sensors, input and so on. So the moment that particular device triggers the controller, I do something that is important, and then I set a flag. So this is basically a flag. Correct? And inside the main loop, I check for the flag. Alright, so we are quite familiar with this. Alright, again, it is not so ideal. Why? Because if, let's say now I set this flag device A request to be true, but in my main loop, I'm here. Alright, then I still need to wait for everything to finish and go back. Alright, it doesn't sort of immediately ask device A code to run. Okay, I still need to wait for the main loop to go one full circle and come back. Okay, so there are ways to make it better, which we will look at. Alright, but this is an easy way of handling a sequential flow of code with interrupts in the background. Okay, now when I say run to completion scheduler, alright, what does it mean? That means you can have some way of storing some additional information for the task. Okay, that means how frequently must I run the task, how long should I release the task, and when is it ready to run. Okay, so you can have some sort of a timer running in the background, a timer interrupt, and the timer interrupt, okay, will basically trigger periodically to tell which task should run next. Okay, in a sense, this is similar to how OS operates. Okay, OS also runs in a similar way where you have a OS tick, okay, that will continuously trigger the OS to decide who should run next. Okay, so this is of course very complicated. So in most cases we do not want to implement something like this. We rather use the OS. Okay, so that's where the OS will come in later on. Okay, now this model again is run to completion. If I say preemptive, means I start something but I'm willing to give up, okay, it halfway to quickly switch to something that is more important. Alright, so again, why it is important? Because you don't have the worst case response time. Okay, you don't need to worry about the worst case response time. The moment a higher priority task comes along, you can switch. Okay, so these are some of the ideas. Okay, so coming back to this task state again, you can see that right now, when I am running a task, okay, I don't necessarily have to run to completion, correct? Why? Because if somebody more important comes along, okay, that means if this isn't the highest priority task, I go back and wait. Okay, if I'm the most important task, then I can run to completion. Okay, so this idea of this task state model allows us to now assign a state to each task to say which particular task will be in which state and who is supposed to run. Okay, so right now this idea is giving you some overview of how the OS works. Okay, so the OS works in this similar concept where you will keep looking at all the tasks that want to run, who is most important and who should run. Okay, so of course that is the general idea. Then we will also look at how we can manage inter-task communication, how we protect memory, how we synchronize and so on. Okay, so that's why this idea of scheduling brings us to the idea of OS. Okay, so what is real time? Okay, real time basically means that you can define a maximum response time for each task. Okay, that means I can give you a specific timing bound and I say that your system will respond within this timing bound that I give you. Okay, now how you define this timing parameter is up to you and what the system must achieve. Okay, so what is inside the OS, okay, like what we looked just now is the scheduler. That's the big part of it which determines how all these different tasks will talk to each other. Okay, and then things like how the inter-process communication synchronization will come in. Okay, at the same time, most OS also provide additional libraries. Okay, file system, network, communication protocol, and so on. Okay, so in terms of timing, okay, so if you look at the static approach, basically this whole chunk means all the tasks will run sequentially, correct, one after another, and whenever an interrupt is triggered, I jump to the interrupt and I come back, jump to the interrupt and come back. Okay, if the non-preemptive will basically mean I run to completion. So in that case, what happens? Whenever I start a task, I am bound by the task time until the next switch comes along. Okay, because I cannot preempt the task. Alright. For the preemptive dynamic, there is basically no fixed timing. Where anytime, anything can happen. Okay, the moment a higher priority task comes along, I will be able to switch. Now, in terms of memory requirements, okay, how much memory do I need? Okay, in the case of the static and the run to completion, in both cases, I know that when I start a task, I will have to complete that particular task. Correct? The only exception is the interrupt. But in the case of the preemptive, which is similar to your OS, I can have all my tasks midway through, correct? I can run task 1, get preempted by task 2, get preempted by task 3, and so on and so on. Okay? Which means that I must have enough memory okay, in my stack space to hold the context of all my tasks. Because there's no guarantee that I will complete any task. Okay, I can run halfway and preempt, and so on. Okay, so that's why the memory, okay, in terms of the stack space, you need enough space to handle all the tasks in your system. Okay, because anytime you can switch from one task to another task. Okay, so the idea of this lecture is just to give you some idea of what is this scheduling concept that we currently have, which is a static, the base thing, okay, static cyclic base scheduling approach, and then from there we move on to the dynamic and preemptive. Okay, so don't worry too much about all this stuff. We will focus on what is important along the way. All right. Okay, so next, today we will do this plus chapter 3 and chapter 4. Okay, chapter 3 I will start also. Okay, chapter 3 is what? Chapter 3 is more of an introduction to this CPU core. Okay, the introduction to the CPU core. Okay, just to give you an idea of what we are dealing with. Okay, so initially when I was preparing all this material a few years ago, I thought that okay, we should introduce assembly language in this. Alright, then I look at the slide, then each chapter became 100 over slides. Then I realized if I go in this direction, I got no time for anything else already. Okay, so I took out everything. So left with only the C part and the OS part. Okay, so let's look at what is this CPU core that we're dealing with. Again, whatever that I'm covering in this particular set of slides is not examinable. It's just to give you an idea only. Okay, it covers more on the lower level architecture and what it really is. Okay, so that you understand what we are dealing with. Okay, so before that, this is a very important thing. What is this? It's something we do every day, correct? Every day, what do? We plug in our phone, okay, maybe once we go back home or what, to charge. Correct? Now, what is the important thing that we want to discuss here? Okay, imagine now you put your phone to plug, to charge, okay, and you come back 1 hour later and the phone never charged. Okay, what do? Can somebody tell me? Okay? Okay, somebody tell me, what do? You plug in your phone, you come back 1 hour later, it doesn't charge. Cry, okay? Besides that, this is an important question, later I see why. Change wire, okay? Anything else you'll do? Turn the switch on, yes? Number one thing, most of the students every time come, say never work, because never press the on button. Okay, it's always the case. Change battery, eat burger, go anywhere, shuttle bus. Okay? Charge in lecture, can. Check wire connection. Alright, so why am I asking this question? Because this is a very important thing that you must have, alright, once you start the labs. Alright, buy a new phone. Okay, so why is this important? Because ultimately, alright, you must learn to solve the issues that you face in the lab. Alright, so when you're year one, generally the TAs will sort of help you along the way. Alright, help you to troubleshoot, check this, check that, and so on. Okay, but okay, in this module, okay, I would like you all to develop more independence. Alright, so if you do something and it doesn't work, okay, try to figure out yourself what is wrong. Alright, so in most cases, you could be the hardware side, it could be the software side. Okay, so you need to decide what you think that you want to do. Alright, so if it doesn't work, okay, check your hardware first. Are the connections correct? Okay, are all the wiring correct? Your power supply? Okay, check that first. Then on the software side, did you configure everything correctly? Alright, what else can you do to troubleshoot? You can use your multimeters, you can use the oscilloscope, check your power levels, check your signals, and so on. Alright, so when you start to do this kind of troubleshooting on your own, you get more confident, correct, in dealing with the hardware, dealing with the software, and you know how to solve the problem. Okay, most likely the TA will know, alright, will be able to tell you the answer, but before you ask the TA, try to solve it first. Okay, try to solve it first, then you approach the TA if you still are stuck. Okay, so I hope you all do that. Okay, so let me go through a quick overview of this. Okay, so this Cortex M0 Plus processor, again, this is all assembly language related, so I will not go into too much detail, just to give you an idea. Okay, so again, the ARM Cortex M0 Plus core is the main processing core of your whole microcontroller, and together with that, we put everything in and we create this microcontroller chip. Okay, so everything, things like your memory, your clock, all these are your peripheral subsystem that come together and give you this complete microcontroller. Okay, so again, this is the whole M0 core. Okay, again, this is more for assembly language, okay, which you will learn later on. Okay, but some of it we will cover in this module as well. Okay, so the ARM, as it is, has what we call a load store architecture. Okay, load store architecture means all your information is in the memory. I need to capture that information, load it into my memory space, internal register, perform the computation, and store the result back. Okay, that's what we call a load store architecture. So it basically involves this three steps. Okay, so in terms of a processor space, okay, your processor only does three things. Okay, no matter how complicated it is, it only does three things. FDE. Can you tell me what's FDE? You would have heard somewhere. The processor only does these three things again and again. Fetch, decode, and execute. Okay, that is the core of any processor. You just fetch, decode, execute. Okay, fetch your instruction, fetch your data, decode, okay, and once you decode, it execute, okay, and part of the execution is maybe to write back and so on. Okay, so this is the main thing, regardless of whichever processor core you use. Okay, so these are again the core registers, which we will not go through in detail, but to give you an idea. So if you look at the assembly language code, in the Kill IDE, you can also look at the assembly language code, alright, which I will show later. You can actually see how your C code is translated to assembly. Okay, so later on, okay, like you said, you're going to learn assembly language. You can also reference back the assembly language that you see here. Okay, so there are general registers. Okay, there's a stack pointer, like I said. Link register is when you branch and link. Okay, like how you jump to a function. When you jump to a function, you need a return address, correct? So that is your branch and link, the link register, and your program counter. Okay, in terms of operating mode, you have two main modes. One is called the thread mode, okay, or the handler mode, okay, depending on whether you are dealing in the normal operation mode or exception. Okay, so again, like I said, don't worry, we will not go through all of this. Okay, in terms of the core registers, these are three registers. Okay, the application register, the interrupt processing register, and execution register. Okay, so we will not go into the details of all these registers. Like I said, this is for assembly language part, but again, these are things that you will see along the way somewhere. Alright, so at least you should know what it means. Alright, these are the core registers. I will not go through this, but you can reference it if you want. Okay, so this is interesting, memory map. Okay, so what is a memory map? Okay, a memory map is basically the entire space your processor can access. Okay, so now if I look at this, is from all zeros to all F, correct? 32-bit. Correct? This is which bus determines this? There are only 3 buses in your processor space, correct? What are the 3 buses? Hey, why every time are you talking Japanese or Korean? What are the 3 buses? Anybody? Your processor architecture only got 3 buses. What are the 3 buses? You can type also in the poll, I can see if you type. Anybody? A1, what is A1? Okay, data bus. Okay, data bus, correct. Another bus is address, correct. Okay, and the last one is what? Control, correct. See, you all know, you all just hiding from me only. Okay, so there's only 3 buses: address bus, data bus, and control bus, which links up your processor to everything else. Alright, so this is what? This is determined by which bus? Your starting address and ending address of all the space you have is determined by which bus? It's your address bus. Okay, your address bus basically determines the entire space that you have. Okay, that means all the memory range that you have. Alright, so from a designer perspective, okay, that means the people who design this chip in NXP, for example, what would they have done? They take this chip, correct? They say, okay, this is the space I have. Okay, so within this space that I have, what are the features I want to add? Okay, what are the features I want to add? So for example, I need memory for my code, I need memory for RAM and so on. So I set aside. Of course, code is always at the lowest address 0 because of your reset vector. Okay, so code always starts from 0. So that is where you keep your permanent storage, correct? Your flash storage. Okay, then you need your RAM space for your code execution, your variables and so on. So you set aside some space. Then you have other space for peripherals. Peripherals are things like all your GPIO, timer, ADC, everything. So all these are hardware blocks within your chip, but they are mapped to certain addresses. Which address we will see later when we look at the data sheet. Okay, so they are all mapped to certain addresses. Okay, now how does this thing work? It is a whole topic by itself. A few years ago, I put that as one of the topic. We will see. If got time, I'll bring it back. Okay, so that is called address decoding. Okay, address decoding means what? That means when I put an address out on the address bus, I must activate somebody, correct? Okay, this address mapped to GPIO port. This address mapped to ADC port. This address mapped to the RAM. Okay, so I need to have some additional hardware somewhere to decode the address to activate the particular peripheral that I want. Okay, so that is a whole topic by itself. Okay, again, if we have time, we will revisit that. Okay, so that is the whole idea. So you have this entire space, and the people who design this controller chip design it this way. That is why the addresses are fixed. All the registers are fixed. Okay, if one day you want to design your own controller by yourself, then you have this space. Correct? You have this address space, and you can decide what you want to put where. Okay, so that is if you are designing on your own. In our case, it is a chip that is already available, so we follow the addresses given to us. Okay, do we really need to know all the addresses? No need. It's already mapped out for us in the library files, which we'll look at later when we look at the code. Okay, Indianness. Okay, so what is this? You all have seen this before, correct? In EBP2. What is Indianness? You all remember? Okay, Little Indian and Big Indian. So what is Little Indian and Big Indian? Alright, so I'll give you a simple example. Okay, so if I say 0x11223344. Okay, if I give you this 32-bit address and I want to store it. Okay, so let's say I start with this address A000, okay, A001, A002, and A003. Okay, so 4 addresses, correct? 4 addresses, and I have a 32-bit data, that means 4 bytes. Okay, how do I store it? You just remember one. You remember one of it, the other one is opposite, correct? Okay, so the one I always remember is simple. LL. What is LL? The least significant byte in the lowest address. LL. Okay, least significant byte in the lowest address. So what is the least significant byte here? 44, correct? Okay, so 44 will go to the lowest address. So 44, 33, 22, and 11. And this is your little Indian. Okay, just remember one. Then the other one is the opposite. The opposite means what? The least significant byte go to the highest address. Okay, so you remember it this way, you won't go wrong. So one is little Indian, one is big Indian. Alright, so why you need to know this? Because some processors may operate in different modes. Okay, in most cases, it may be transparent to you. But when it becomes an issue is, if you remember in EPP2, inter-process communication, correct? When RPi talk to Arduino, correct? Or one processor is using big Indian, you talk to another processor is using little Indian. Okay, so in those kind of cases, then it becomes an issue if you do not know this. Okay, so just be aware that there is this format. In our case, it does not affect us, alright, because everything is within one computing space, alright, but it's good to know so that you have to deal with it, you know what it is. Okay, ARM is generally little Indian, so we don't need to worry. Everything is little Indian. Okay, ARM, thumb, and thumb 2. Okay, so just some quick history. Okay, so ARM started many years ago. Okay, ARM is which country one? You all should know, right? From which country? UK, correct? It's a UK-based company. All right. So it started off as a small research project, and then it became very big after that. Alright, and of course now all over the world everybody is using ARM. Okay, so when ARM came out, originally it was a 32-bit system many years ago. But what happened is it's always economics, right? Economics of business. Alright, when ARM came out, it was 32-bit, but at that point of time, 32-bit memory was very expensive. Okay, so the manufacturers who wanted to integrate ARM preferred 16-bit memory. For lower cost. So to support that, they made thumb. So it's ARM and thumb. 32-bit, 16-bit. Okay, so that is how they came from ARM to thumb. Okay, so they say 32-bit becomes 16-bit. Okay, and for a while it was okay, and then over time the memory prices came down. Alright, and people say, okay, I want to switch back to 32-bit. Okay, but now you have 32-bit code and 16-bit code. What? Correct? How to mix? Okay, so to make everybody happy, they came out with thumb 2. Okay, which means that now you can mix both together. Okay, again, does it affect you? No, but when you're doing assembly language code, then you need to look at it. Okay, in our case, since you're writing in C, it's fine, no need to worry. Okay, instruction set, again, it's all assembly language part, no need to worry, I will not go through in detail. Okay, so before I go to I/O, just one thing, like, if you want, you can 3D print a case for your KL25Z board, okay, with whatever ports that you want, and you know, if you want to put it in a nice way. All right. You can also fabricate your own PCB. In the past, students have fabricated their own PCB for the entire project. Okay, which I will bring along next week. Okay, so let me move on. Okay, never mind. Let's go for a 10 minutes break. Wow, now only happy everybody. 10 minutes break. Okay, now it's 10. Okay, come back 11. Okay, come back 11. Then we will start GPIO and then we will look at the lab. Okay? Okay, so in the meantime, you need to download these two datasheets from the Canvas. So the Canvas, under the project, there is two datasheets. Go and download and keep. You need it for reference. Okay, so go for a break. I will come back 11. Okay, if any questions, you can put in the poll. Okay, I will still answer later. Yeah.
I just wanted to ask you, so not following like every single step, so I'd like to go into it.
Okay.
So I wanted to ask if you could recommend like the resources and
Okay, so this two Okay, so let's start. Okay, so like I said just now, please download these two data sheet and keep with you from download from Canvas. One is this, the KR25Z user manual. Okay, this is specific to the board that we are having, and this is the actual data sheet of the microcontroller. So it's 807 pages, so we can't sleep over the weekend, you just keep reading and reading and reading. Okay, no, nobody reads the whole data sheet. Okay, you only go and extract, okay, what is really important. Okay, so if you remember the first lecture I talked to you about the project that I did when I was a student. That time is the Intel processor, also 600 pages. Okay, but no computer at that time, correct? So we print out double-sided, smaller one, and carry around in the bag everywhere. Okay, one big chunk of data sheet everywhere in my bag all the time. Okay, so now it's easier. You can just do online. Okay, so let's start with GPIO. Alright, so usually when you start out with any microcontroller that is new, okay, whenever you start any microcontroller is new, usually the thing that you want to try out first is the GPIO. Okay, you want to get the GPIO up and running because that is one of the easiest peripherals, okay, that you can deal with. You can just connect a switch or LED and just confirm that it's working. And in most development boards, okay, usually one of the GPIO or two of the GPIO may be connected to some LED on board already. Okay, so they make it easier for you to do some initial testing. Okay, so we're going to look up at some overview on GPIO, basic and so on. Okay, so just now there's a question whether the two topics is okay. So the topic on the Cortex M0 Plus core is not tested. Okay, but the earlier one on the scheduling and so on, you need to just have some idea of what is scheduling about. Alright. Okay, but the one on the Cortex M0 Plus core, that one is I will not ask anything on that. Okay, so let me share with you a quick life hack. Okay, so along the way I will share some interesting things which, I mean, you have a career guidance counselor and all those things, correct? Alright, so think of it something like that. Only thing is from somebody who has been there, done that, so I can share some other stories as well. Okay, so one of the important life hack, when you graduate later on, when you work or maybe you set up your own company, one of the important things that you must always remember to do. Okay, be the bearer of good news. Okay, what do I mean by this? Be the bearer of good news. Okay, so imagine that you are working in a company. Okay, imagine you are a manager, correct, and you have an employee. And every time the employee come and see you, he come and complain. He say, "Alamak, the board not working, the test failed, this thing happened, the thing is delayed, the code not working." The next time you see him, what do you want to do? You want to run away. You don't want to see him, correct? Because the moment you see that person, you know it's bad news. Okay? Don't be like that. Be the person who go and tells your boss the good stuff. Hey, this is not working. We fixed the problem already. Okay? The board is ready. You know? So, come with good news. Because when you relate yourself with good news, people want to see you. Have an expectation that, okay, if this person comes means, okay, there's something good to hear. Okay, so always come with good news. If you have bad news, you cannot hide it but you can always say it in a nice way also. Alright? So always remember, try to relate yourself with good news. Okay, so your colleagues or whoever you work with want to be with you, want to hear what you have to say. So always be the bearer of good news. So this is a life hack for today. Every week I try to share something. Okay. So some basic concept. Switch and LED. Okay. Now let me ask a simple question. If you all don't know this, I must tell we saying EPP1 never work properly for you. This switch, this circuit here, what kind of pulse will I generate? Will I generate a pulse like this or pulse like this? Okay, option A or option B? You all can put in the chat. B or A? B for burger. Okay, so a few is B. Right, you have a colorful B also. Any other answer? Okay, so let's see our beta also. Okay, so let's see. So what is the default value? Okay, if I connect this to a GPIO pin, okay, if I connect to a GPIO pin over here, what is the default voltage I will read? Will it be high or low? Where is it connected to? It's connected to what? VCC, correct? Because there is a direct connection between here to your positive, correct? So by default, if I don't do anything, I will read a high voltage, correct? Then when I press the switch, what happens? When I press the switch, I'm creating a short circuit to ground, correct? Alright, the pull-up is still there, but the point where I'm reading the voltage is the point where it's connected to ground, correct? Okay, so because of that, when I press the switch, I will go low, correct? Okay, then when I hold it, it's still low. When I release, it will go high. Correct? Okay, so these are simple things you must know. As computer engineers, you must know how to relate a schematic to the code that you're going to write. Okay, many times the problem is always you write the code, but your code never matches the hardware that you have. Alright, so you must always make sure your hardware and your code match up. Okay, then it will work. Okay, same thing for the LED. Okay, yesterday I had a EPP2 lab. And then the guy say he forget LED which one is positive, which one is negative. Please don't be like that, Okay? LED positive and negative you should know, correct? So in this case, okay, to activate these two LED, must it be a high or a low? Do I need to provide a high or a low over here to activate these two LED? Should be a high, correct? Because if I put a positive, the current will flow, okay, through the LED to ground. Okay, again, you must look and understand that it can be both ways, correct? I can connect it the other way around, then it will become an active low, correct? In this case, it's an active high configuration. So you just need to know the hardware you're dealing with. Okay, now the GPIO ports. Okay, now as always, the actual controller you have can have a lot of stuff. Okay, but when the manufacturer takes this controller and puts it on a board for you, they will try to bring out as much as they can to make your prototyping easy for you, which means that some of the pins you may access, some you cannot access. Okay, it's always the case for any microcontroller. Okay, so first thing, can you go to your datasheet? I asked you to download datasheet, right? Tell me where you can find the GPIO section. Which section is it? Okay, so if you open up a data sheet for this, okay, you go down, your GPIO section is, where is it? Chapter 41. Okay, chapter 41. Okay, so you must know how to find the information that you want, okay, in your data sheet. Alright, so let's come back here. Okay, so whatever I'm showing here is all extracted from the data sheet. Okay, so you must know and be comfortable with extracting this information by yourself. Okay, in the future you may use a different controller, a different board, so you must know how to extract the information. So when I look at the data sheet, I should know how to read certain things, extract the information on how do I control it, how do I use it. Okay, so this is a general idea of a GPIO pin. Alright, we are not going to go into all the circuitry, but it sort of gives you an idea of all the different registers involved. So you can see here there's a data direction register, there are some registers to control the output. Okay, there's also a register for the input. Alright, so this small pin here, this is the actual pin that you can connect to. An actual pin you can connect to, but in the back end, inside the controller, you have all this other stuff. Okay, so what are all the registers that you need? Okay, so these are all the registers that you need, okay, inside your, to control any of the ports. Okay, so how many different ports are there? Here I am showing you GPIO A. Okay, now how many other ports are there? A to what? Okay, there are ports A to E. Okay, but not all the ports you can access all the pins. Okay, some ports you can maybe only access some of the pins. Okay, so all of this you need to be aware of when we do the lab. Okay, so each of these ports, okay, as you can see, it is tied to an address. Okay, these addresses are just now what I talked about just now, where the designer of this controller already decide that I want to map peripherals to this address, and of all the different peripherals, GPIO is in these address locations. Okay, so this mapping is already done for us. Okay, for all the registers associated with each peripheral. Okay, now if you look through, okay, the entire data sheet. Okay, again let me show this over here so you can sort of relate it. Okay, so if I look down here, all the information is here. So you can see down here that I have GPIO A, GPIO B, GPIO C, and so on. Okay, and all of them have the same set of registers. The same set of registers, but for all the different ports, depending on which port. So same thing like Arduino Uno, correct? You also have port B, port C, port D, correct? And each of those ports also have their own set of registers. So the same concept is over here. Only thing here you have more registers. Okay, now if you look down here, you will see that I have a bunch of registers, and I want you to look at this point here. Okay, you notice that for port B, okay, or for all the ports, the ending of one port, you don't immediately start the next port. There's a gap, correct? There's a gap in the address. It is not always, see, for each of this is always plus 4 bytes. Correct? Because each register is 32-bit. Okay, so every address, increments by 4 bytes because every register is 32 bits, 4 bytes. Okay? But why is it that when I end one register, one port, when I go to the next port, I have a bigger gap? Why don't I just increment by 4? I can save space, correct? If I just increment by 4, I can save space. But why do I leave such a big gap? Okay? From port B to port C. Same thing from port A to port B. So every time I go from one port to another port, I have a bigger gap. Why don't I just increment by 4? Okay? Okay, why? Very simple. It's always this. It always comes down to money. Why money? Because it's a lot of money and investment to come up with your own microcontroller, correct? Okay, come up with a microcontroller that you can sell. Now, after NXP, for example, comes out with this microcontroller, this KL25Z board, and they sell it to you, what do they want to do? Do they want to start the whole process all over again and redesign a new controller and sell it to you? No. Correct? What do they want to do? They want to make very small changes and sell you, wow, we did a lot of things. So you need to pay a premium. Correct? So how do I do that? I intentionally leave gaps in my design for me to upgrade. So I upgrade the gaps without changing the whole thing, correct? Okay, so what can I do? I can say, okay, I can add in maybe 2 or 3 more registers here to do something else. But I already have reserved the space for me. So I don't need to go and redesign the whole address space, okay, for a new design. Okay, it's the same thing, correct? When you buy a Samsung phone to another Samsung phone, is it really a big change? No, what? Correct? Apple just changed the lens also with a new phone. Correct? So it's always minute changes, but they advertise it very big. Why? Because the design already keep all these gaps for you. Correct? And then you just fill the gaps to say it's a new design. Okay, it's a new product. Okay, so coming back to this, the registers, again, every controller has its own set of registers. For our case, okay, these are stuff which you all know and comfortable with, so I will not go through so much. Their direction register is either input or output. In our case, input is 0, output is 1. Okay, to write to a register, there are four different ways of doing it. Okay, I can directly write to what you call a PDOR register. That means I can write a 1 or a 0. If I want, I can toggle it by keep writing a 1 to it. Okay, I can keep toggling the bit by writing a 1, or I can use the clear, or I can use the set. Okay, so it's up to you which register you want to use, as long as you know what you want to do. It's fine. When I want to read from the register, say I connect to a switch, then I use the PDIR register, port data input register. Okay, so these are some pseudo code. Okay, I will skip this part. Alright, now where is the mapping of all these registers to the code? Okay, so let me show it to you in the KL25 that way around. Okay, so this is the header file that you will see where all the definitions for all the registers and the addresses are all mapped there. Okay, so I will show you in a while where all this maps to, how we get the base address, everything. Okay, I'll show you in the code. Okay. Okay, so this is for next week's lab, okay, on GPR. The code I'll go through in a while. I don't need to worry about the code. Okay, now for each of these registers, okay, so for example, when you look at port B, for example, if I go to definition, you can see that the definition is all inside this header file, mkl25z4.h. Okay, and if I go deeper into this definition, each of this is a GPIO type. Okay, and if I go deeper into that, you can see that it maps to this. Okay, now this sequence of registers, PDOR, PSOR, PCOR, actually comes back to where? Okay, comes back to let me try and so you can see the sequence here. This sequence here is directly following this sequence here, correct? PDOR, PSOR, PCOR, and so on. Okay? So what is the objective? Why do we do it this way? That means all I need to do is, I always have to point to the base address, correct? I just need to point to the base address of each of the port, and automatically everything falls in place. Why does it fall in place? Because each of this variable is 32-bit, which matches my register size, correct? Okay, so that is how they define all these structures in your header file. Okay, they will arrange the variables in your structure so that it matches exactly the way it is designed in the hardware. Okay, so when I write the GPIO configuration here, the base automatically point to a particular address, and everything else will just fall in place, where everything is 32 bits. Okay, so that is how the whole structure is laid out. Okay, now this address, PTA base and so on, this okay, is again defined based on the data sheet. Okay, so in the data sheet, we already know where is the starting address of each of these registers, correct? Okay, so the base register is always the first register for the whole sequence of registers. And since everything is defined in a structure, everything is easily accessible. Alright, so this is just to give you the idea how all this thing falls in place, so you can appreciate what you are seeing in the code later on. Okay, so let me just run through this. This one we have seen before in EBP 2, okay, on bit masking, bit shifting and so on, but let me just run through this because you will see this kind of code very frequently. Okay, so let me okay, so this idea of bit masking and bit shifting. Okay, so I just want to quickly run through this so you know how it looks like. Okay, this shifting is what? Okay, when I say 1 shift left 90 means what? 1 is 1, which is all zeros, correct? Okay, and when I say shift left by 19 means what? That means the 1 is shifting left by 19 bits, correct? Okay, so effectively this 1 will come to bit position 19. Alright? Same thing over here. When I say 1 shift left 13 means the 1 will shift until it comes to bit position 13. Correct? Okay, and when I do an OR operation, what happens? That means bit 19 and bit 13 both will become 1, correct? Everything else will become 0. Alright, so these are ways in which your code will be written quite frequently, so you need to be familiar with it. Alright, so very often we will use what we call a mask to shift a 1 to a particular position. Okay, why you want to do that? To make it easier when you want to look or set or clear any particular bit inside a 32-bit word. Alright, so that is the first thing you must know, the masking and the shifting. Alright, now to set any particular bit, in a register, you can use the OR equal. Okay, because when you do an OR with a 1 means what? The answer is always a 1, correct? Now we do a logical OR with a 1, then your answer is always a 1. When you want to clear a bit, what must you do? You must do a AND with what? AND with a 0 is to clear it to 0, correct? Okay, so these are a few things that you must know. So set a bit, clear a bit. Okay, so how do I clear a bit? I AND with the complement of mask full. Okay, so for example, if I say I want to clear, okay, if I say I want to clear bit 5. Okay, if I say I want to clear bit 5, then I say AND equals to complement of mask 5. Okay, why mask 5? So the 1 will shift left by 5 bit. Correct? To come to here. Alright, and when I do the complement, what will happen? The 1 will become a 0, correct? So when I do the complement over here, the 1 will become a 0 and everything else will become a 1. Correct? And when I finally do the AND operation, so I do an AND with this, what will happen? This particular bit will become 0, correct? And all the other bits will be retained. Correct? These are not new, these are things we have done before in your EBP2. Your bit masking, your shifting, setting a particular bit, clearing a particular bit. All these are things you should be comfortable with. Okay? Okay, so one of the other things about the KL257 microcontroller is this thing called clock gating, okay, or clocking, which is applicable to all peripherals, not only GPIO. That means before I can use a GPIO or any peripheral block, I need to enable power to that particular peripheral block. Okay, when I say enable power means I need to enable the clock. Okay, so your Arduino, okay, also has this feature. Only thing is the Arduino is by default everything is on. Okay, so we don't do this step. Alright, so in some controllers by default everything is on. In this case the default is everything is off. Okay, so if I want to use any particular subsystem, I need to switch on the power first or switch on the clock. Alright, now where is this clock information? Okay, it is in a series of registers called SCGC, clock gating registers. Okay, so there's SCGC, okay, 1, 2, 3, 4, 5, 6 and so on. Okay, it's all depend on what particular register that you want to set or clear to. Alright, now to set any particular register or clear it, we can use the hash defined clocking logic here. Okay, so don't worry on this one, I'll come to this in a while when we look at the code. Okay, now where is this? Okay, where is this in your data sheet so that you know what I'm talking about? Okay, so if you search for ICGC file, okay, you will see that you come to this register, and in that it is the clock gating for all the ports. Okay, so if I want to use any of the ports, I need to first enable the clock to the register, then only I can use the ports. Alright, so this is the additional step you must do. Okay, so okay, now the other thing that you must do is the multiplexing. So there's a few things you must do before you can use the pin. First you need to enable the clock. After you enable the clock, you need to configure the multiplex. So you are already familiar with the idea that every pin has multiple functions, correct? Okay, every pin has multiple functions, so we need to decide which of the function that you want to use it for. Alright, so in this example, okay, or in all the GPIO pins, you have what you call a pin control register, PCR register, which you can configure the multiplex function that you want. Alright, so there are a few different options, okay, depending on which alternative function that you are looking for. Alright, now where is this in your data sheet? Okay, so again, let me show you here. Okay, so if you search for PCR register, you will come to this. And for now, we are interested in the mux option. Okay, so if you look at the mux option, you can 001 is the GPIO function, and everything else is chip specific. Okay, chip specific. Okay, so where do I see this? Okay, it's also a data sheet. Okay, but this one we will look at that later. For now, we know that if I want GPIO, I need to put it as 001. Okay, so don't worry, I know first time when you look at all this is like overwhelming, too many things. Okay, but after a while you will be used to it already. You will know that I need to do this and so on. Okay, so it's always the first step that is always tough. Okay, after that you'll be fine. Okay, so instead of going through all this, I will go through the actual code, for the lab. Alright, then it will be easier for you to relate. Okay, so what are you supposed to do in the lab for next week? Okay, you're supposed to program your port. Okay, you're supposed to program your port, okay, to control the LED on board. Okay, so I've given you the steps how to create a new project, everything. Okay, so yesterday those who collected the board confirmed already that the board is working. So no problem. We are all safe. Okay, so these are all the ways to set up the project. Now, for the board, you have this other data sheet. Okay, the actual Freedom Board information. So we are interested in, okay, so it gives you all the information on the whole board, the pin out, everything, which we will look at. Okay, but for now, we are interested in the LED portion because we want to control the LED. Okay, the RGB LED. So this is the circuit given. Okay, so when I look at this circuit given, okay, for the RGB LED, you can see the information, correct? The tree is a single RGB LED, alright, and it's connected to 3 different pins. Port B, pin 18, correct? Okay, port B, pin 18, port B, pin 19, and this D13, which is your port D1. Okay, so I have 3 pins, okay, where I need to configure in my KL25Z. So to switch on the LED, should I put a 1 or a 0 to these 3 pins? Looking at the hardware, should I put a 1 or a 0? Should be a 0, correct? Why? Because all the anode is connected to the 3V3. Correct? The 3 anode of the LED is connected to the positive. That means if I want to switch on the LED, I must put a 0 to control the LED. Okay, so this is what I said. You must be comfortable with looking at the hardware to know what exactly is the code that you need to write. Okay, so let me go through the code first, okay, and then we will see the demo in a while. Okay, so this is the code, okay, which I have written. Okay, I'll go through step by step. Okay, only for the first slide, I'll go through step by step. So you understand the whole sequence, how it works. Subsequently, you should be able to do it. Okay, now, so in my main function, I'm going to call the init GPIO function. Alright, so the init GPIO function is to set up everything. Okay, so the first thing that I need to set up is my clock. Okay, I'm setting my SCGC5 register over here. Okay, and I'm doing a SCGC5 port B mask and SCGC5 port D mask. Okay, now where is all this? Where did all this come from? Alright, because you need to know where all this comes from. So all of this comes from my header file. Okay, so if I go and search for this, go to the definition of this, it tells me that this mask is 0x400. Okay, 0x400, that is my port B mask. Okay, and if I look at my port D mask is 0x1000, correct? Okay, so let's look at this number. So my port B mask is 0x400 and this is 0x1000, correct? Okay, so when I all these two together, I'll get 0x. So if I do an OR here, I'll get 0x1400, correct? Alright, 0x1400. Now if I just try to look at this, so this will be 4 is 0100 and this will be 0001, correct? Okay, and in terms of bit position, this is 0 to 7, so this will be 8, 9, this will be 10, and this will be 12, correct? Bit position 10 and 12, okay, because this is 0 to 7, correct? Okay, so the 4 and 1 will be bit 10 and bit 12. So what does that relate to? Okay, in terms of SCGC5. Okay, so you must see how everything come together, then you will see that why we are doing this. Okay, so pin 10 and pin 12, correct, relate to port B and port D, correct? I relate to port B and port D. That means what am I doing here? I am enabling the clock. Okay, I am enabling the clock for the port B and port D in this first line. Can you see? Because SCGC5 register is to enable the clock. So to enable the clock, I must write a 1 to the particular pin there. Okay, now if I don't use this built-in mask, means what? That means I need to manually put in my own binary or hexadecimal, correct? But since the header file already declared everything for me, my life is easier, correct? Okay, I just put everything there. Now this is to do what? Okay, so this line here, okay, is to say that for port B, the PCR register for red LED. What is red LED? The red LED is defined as 18. Okay, because it's port B pin 18, correct? So for port B, okay, pin 18, what am I doing? I am first clearing the port PCR mux mask. Okay, what am I doing here? So let's look at it. So if I go to a definition of this, okay, it is 0x700, correct? 0x700, that means 0x700 means this is, if I just look at this, is 0111. So this is bit 8, 9 and 10, correct? Bit 8, 9 and 10 of the port PCR mux register. Okay, now let's look at the port PCR mux register, then we will see where this comes in. So can you see 8, 9, 10 is a mux? Okay, so what am I doing there? I am actually clearing the 3 bits because it's n of the complement, correct? Okay, it is n of the complement here, which means I am clearing my 3 bits, correct? So this first line here, what am I doing? I clear for bit 10 to 8, correct? I clear the 3 bits that is used for the multiplexing, and then in this line what do? I do a OR with port PCR mux 1. So what is port PCR mux 1? So this is this definition here. So this is a very long definition here, okay, which you can go and see later, but basically what it does is, it is taking this value 1, correct? It's taking this value 1, and what is it doing? It is shifting it, correct? Shifting it to where? Based on how many bits? How many bits to the left? 8 bits. Why 8 bits? Because it is 8, 9, 10, correct? In the register, the mux bits are 8, 9 and 10. So I'm taking the value 1 and shifting it to the left by 8 bits, correct? So it comes to the position 8, 9 and 10, and then I'm doing a AND with the mask. So I'm making sure that only the 3 bits are updated. Okay, so basically what I'm doing is, I am selecting GPIO function, correct? Because in the mux setting, if it is 001, it is GPIO. Okay, so that is what I'm doing. Okay, so like I said, you need to go back and go through all of this again. Then you sort of make sense. Okay, but for now, you just take it that understand the steps involved. Okay, so first I set the power, next I set the configuration. Now after I set the configuration, so I do this for all the 3 LED, then the last step is to set the data direction. So the data direction is the DDR register, correct? And in this case, I set everything to 1 because 1 is the output. Okay, so I set the data direction register for both port B and for port D to make sure that both of these ports are now configured as output. Okay, for these pins. Okay, so that is the setup part. the setup part of the code. Now what is the next step I do? To control the LED, okay, I call this LED mapping function, and this LED control basically, in my case, in this example, I use the PCOR register. You can use any register you like. Okay, why I use PCOR? Because I clear, correct? I need to write a 0 to switch on the LED. Okay, so depending on which LED that I want to talk to or I want to control, I configure that particular port and PCOR register to on or off the LED. Okay, and to off, I do the SOR, because when I write a 1, I will be off. If I write a 0, it will be on. Okay, so that is the general idea of how this whole code works. Okay, so for any peripheral, it's always the same thing. First, you enable the clock, then you do all the necessary configuration. In this case, for GPIO, you have to do PCR, okay, in that direction, and after that, then you can write your code to control the actual register to on or off the pin. Okay, so let me just show you how the whole thing works over here. Okay, so after you write your code, so you just follow all the steps. Okay, so after you build, you can debug. Okay, so when I run this code, okay, it will basically show the LED blinking. So there's a single LED with RGB. Okay, so there is a delay function here, which I also uploaded to Canvas. This delay function is just to provide a delay so you can see the blinking. Okay, if you don't put the delay, what happens? You only see white light. What? RGB is white, correct? So if you don't put a delay, you see white light. Okay, so you put a delay so you can see it toggling between the different LED. Okay, so again, I know it is overwhelming, a lot of stuff, okay, but after a while you get used to it. Okay, you will know that, okay, these are all the things I need to do. Alright, so for the first lab next week, okay, this is the objective, right? You're supposed to come up, okay, with this to just be familiarized with the whole flow, how to create a project, okay, how to write your own device driver code. In this case, the device driver is your GPIO library, okay, and you control the RGB LED. Okay, you can write it whichever way you like, okay, but the steps must be important, you must follow. The power, the PCR, okay, the data direction, and finally the actual register. Okay, so any questions you can ask me or you can put in the poll if you still have. Alright, if not, thank you very much, okay, and now I will see you all next week, okay.